Right. I said that one of the 5 things that you definitely need to know in studying electric circuits is Ohm's law, which is a funny thing to say because Ohm's law isn't always true, as we will see later. Ohm's law, V equals IR, states that the potential difference through an ohmic conductor, so as I say, it's not always true, it's only true for ohmic conductors. And it's only true at constant temperature. If either of those things vary, then actually it doesn't strictly apply. But where it does apply, it means that the potential difference V is directly proportional to the current through it. Okay? Which is lovely. Because it means, look, if I plot I against V, often you do plot I against V, which is a little bit annoying because if we plotted V against I, then the gradient would be equal to the resistance, but that's not quite true. Sadly, it is instead the case that because R is delta V over delta I, R is inverse gradient of this graph. Okay, so if this graph is steep, that's actually a good thing, because it means the resistance is low. And if this graph is shallow, that's a bad thing, because it means if this graph is shallow, it means that even if you increase the voltage by loads, you pile in more and more energy, you're sort of pumping the electrons through as hard as you can. Actually, it doesn't really do much. There's only a small increase in current, which is sad. Sad to see the fruits of your labor so squandered. Okie dokie. How would we obtain this graph is a good question. So if I've got, and this is an experimental setup that's probably worth being pretty familiar with, because it's how we test any electrical component, really. So I've got my test resistor. I want to input into it various voltages and then measure current, or vice versa. It doesn't really matter, as long as it's a complete data set. So I provide a voltage. Some of that voltage will be lost on this variable resistor. That's what that symbol means. If it's got an arrow through it, it's a variable resistor. And then the rest will be monitored in terms of the voltage spent across this resistor. We attach a voltmeter in parallel to our test resistor. And that will record our measured values of V. And we put an ammeter to measure the current. Yep. We then vary our resistor, which will the effect of varying the variable resistor when the variable resistor is set to a low setting, then nearly all of this V here, V in, we might call it initial velocity, not velocity, voltage. When the variable resistor is low, most of this will be spent here at the test resistor. When the variable resistor is set high, then not much voltage will be spent on our test resistor. And so we can get the full sort of spread here. Okay. Right, moving on. Ooh, sorry, that was a bit of a lag. We've so far made a frankly bold assumption that temperature and resistance are constant, but that's just not the case. A bulb filament, for example, heats up as current goes through it. A resistor heats up as current goes through it. We looked at the microscopic explanation for this. There's electrons as the current increases. They bump into the positive ions, which increases the temperature, which means that there's even more collisions, so the resistance has increased. What a nightmare. The result is that although at low currents, Ohm's law more or less does apply. As you get higher and higher, the resistance increases, which means, again, remember that shallow on our IV graphs is bad, means high resistance, and steep is good. It means that you end up with a graph more like this rather than a straight line. Previous slide, we had a nice straight line, but the truth of the matter is that if you go high enough, it won't be linear anymore. Ugh. Instead, it will be this horrible curve, for which we do not have, or at least at A level, we don't give you an equation for that curve. So it's not proportional. I is not proportional to voltage, and therefore it is non-ohmic, is what we call it. Okay. Right. Let's do an exam question. And then I will try and talk a little bit more about voltage, actually, just to hammer home the concepts. How are we doing for time? Okay, let's pick up the pace a little bit. Describe a method to accurately determine the resistance of a fixed resistor. 5 marks. Oh, describe a method. So this is one of our experiment planning. Fortunately, this is actually more or less what I just talked about. If it says describe a method that's 5 marks, I think we'd better do a diagram. Luckily for us, there's very strong conventions in circuits as to how to draw a circuit, and it's, you know, it doesn't rely on us being creative in any way. We can draw our circuit just the same here. 2 marks, in fact, for the correct components, for the correct layouts. It's not necessarily obvious. I think a lot of students would be like, oh, can't we just have a variable battery or a variable cell? You commercially can buy those things and you will use them in school. You have a power pack and you can change the voltage, and that's lovely. But for the purpose of a circuit diagram, you've got to draw that separately. Your power pack, what it essentially has in it is either a series of fixed cells, if it's a battery operated one, but most of them are plugged into the mains. So what they have in them are a series of resistors, which essentially function the same way that the pair of these two function. So you can't escape, I'm afraid. You do have to draw your variable resistor separately. And then the remaining 3 marks will be for describing a method. So use the variable resistor to adjust the current, and then with the ammeter, measure the current, and with the voltmeter, measure the voltage, and repeat your readings and sort of use the variable resistor to increase the current, and take another reading, and so on and so forth. Plot the graph, and then the inverse of the gradient of that graph will be the resistance. Sure enough, what have we got? Use the variable resistor to adjust current and potential difference in steps, and record values each step. Love it. Plot an IV graph with data and determine resistance from the reciprocal of gradient. The reciprocal, oh, what a word, what a word. That just means 1 over the gradient. Okay. It says describe a method to accurately determine. If we're planning an experiment, this question doesn't explicitly tell us, you know, consider safety or whatever, or consider errors, but it's good practice to always talk about those anyway, especially errors. So sources of error, make sure you keep the lab at fixed temperature. Your voltmeter should have a very high resistance, and your ammeter should have a very low resistance. The reason for that is if your voltmeter had any sort of resistance, like real resistance, if it didn't have like very, very high resistance, the ideal voltmeter has infinite resistance. because we don't want, if the current is flowing this direction, remember the electrons are flowing this direction, but the current is flowing this direction. We don't want to siphon off any current along here because that will affect how much current is truly going through our resistor, which is not the same as what we're measuring here. And so it's all a bit of a disaster. For similar reasons, if our ammeter has some resistance, then it's going to affect how much current actually reaches the resistor as well. And so it'll affect our readings. So for that reason, the ideal ammeter has no resistance, and the ideal voltmeter has infinite resistance. Oh, we could also say use current in a range such that the conductor remains ohmic. Great point. Love it.